hope you're still awake a little bit, and if you're not, I assume there are going to be some music, right? Miro?
Yes, absolutely.
So there are going to be some music.
Yes.
Okay.
And
So I
let's
hope
check if the music is on.
Yeah, that's a good idea. So,
Yeah, it should be on.
so do you play drums?
Yeah, I play different instruments, sometimes kitchen pots, sometimes bottles, whatever I find around. And needless to say, I'm the most favorite neighbor in the entire building.
Okay, so I hope you won't play pot music. What's that?
No, I don't have my equipment this time. So.
Okay, so let's hope for nice music and give a round of applause to Miro on stage.
Okay. Thank you. My name is Miroslav Jonas. I'm a developer productivity engineer at NX. And since my early childhood, I have been driven by my 3 core passions. My first passion is solving puzzles, which is what got me into software engineering in the first place. My second passion is sharing knowledge, which is what got me here on stage, being a recreational speaker at the conferences, also occasional trainer, and a serial meetup organizer. And finally, my third big passion is art, both as a consumer but also as a creator. Now, from different types of art, one that I'm probably the most passionate about is music. So how many of you have ever tried playing an instrument or is actively playing an instrument? Oh, cool, amazing. So yeah, for those of you that don't play a physical instrument, mobile phones and computers are also considered instruments these days, so don't feel left out. So when I was a kid, I found out about this world of electronic music in the late 80s and early 90s. And I was puzzled by the sound that I heard. I heard those synthesizers, and I wanted to learn how to make this sound, how to make this type of music. So I was trying to record samples from cassettes, playing over the cassettes, trying to play piano on top to try to make my music, but it didn't really work out. And I heard that there are people who make music on computer. So this was my first computer. It didn't have a sound card at all, but it had QuickBasic installed. And this was one of the first programs that I created. This is actually a sequence of notes. So if you play this in a QuickBasic, it would sound like this. Recognize the tune? I actually spent crazy amount of time trying to come up with my own melodies just using this buzzer. But then a couple of years later and one computer later, I found out about this intoxicating world of music trackers, and then I spent unhealthy amount of time creating my own music in Fast Tracker, which was my most favorite software ever built. But at that point, I was also aspiring programmer, and I knew Pascal, and I knew that Fast Tracker was written in Pascal, so I was like, I should build one. I wasn't satisfied with just making music, I wanted to make tools for making music. But I also found out that majority of the core parts of this software were written in assembler, and being a teenager at the time, well, let's just say I had some other interests as well than learning assembler at home. So I looked further, and I also found out this tool, which is a very basic drum machine. It has 6 tracks, not many effects that you can apply, so it's a fairly simplified workflow. And I learned that it was written by a student. And in my mind back then, it meant anyone can build it if student can build it. Right? I was naive, of course. So in the last couple of years, I tried to build my own groovebox. First, I tried with Delphi, which was the advanced type of Pascal. I had this thick Delphi Bible, which nowadays can be taken away from you at the airport as a cold weapon. Needless to say, there was nothing in that book that can help you to actually write software like this. Also, the documentation in the IDE was just useless. My next try was in ActionScript. That also didn't work well. I did actually produce sound through it, but ActionScript, part of the Flash being primarily graphical tool, was preoccupied with keeping the visual frames in sync while ignoring the music. So it could happen that the rhythm was going and then afterwards, after some time, it went out of sync, it would drop some beats, so it was a complete disaster. And computers were fairly slower back then, and Flash was very memory hungry. But then COVID came, and I decided, okay, this is time to finally build that Groovebox. So I started looking into WebAudio API in JavaScript, and this is how you normally produce sound. So first, you need the audio context, you create an instance, and then we need to load the file. For example, we want to play the WAV file, so we load it with fetch. We convert the results to array buffer, and then we decode that array buffer using our context into the sound. And then we simply feed it to a buffer node. We connect it to our output, which is the sound card, and then we press the start. And that sounds something like this. So you can play it, you can stop it, and you can basically select any song. Then I was thinking, okay, if I can play one song, what if I can play multiple songs at the same time so I can create my own Groovebox? But playing just sound wasn't enough. I need to do something more with it. I need some effects. So I was looking into, okay, what else can I do with WebAudio? It turns out there's a bunch of audio nodes that you can use. You can create a gain to control the volume, and then you simply connect it in between your source and your output. But you could also create low-pass filter. For those of you that don't know what low-pass filter is, you will hear it in a second. And basically, we can then control different nodes in between. We kind of chain them. Some of those nodes can have multiple inputs. Some of those can be just bridge between different nodes. And again, this is how that sounds. So here we have our low-pass filter and our volume, and again, the same song. And now you can hear the effect. You probably heard it on some parties or in some TV shows where they use this effect to kind of silence the sound. It's basically what you hear if your neighbor is having a party and you're listening through the walls. So you like hear something like this. It's kind of muffled sound. And you can connect, again, a bunch of different things. You can also build your own synth. So I can take a simple oscillator node, I can set it to sine. I can set it a frequency, which is basically the node that I want to play. In this case, 440 is A4 node, just the basic node for the synth. And again, we connect it to our gain and to our output. And we get something like this. But what I can do, I can then chain 3 oscillators where the second and the third are slightly detuned. So they're playing the same frequency, but slightly off. And it produces this richer sound. But I can also then add reverb. I can add some Moog filter. And then we have some better sound. So we can also control the sustain and release. And you can get something like this. Oh, sorry. So for fans of Underworld, you might recognize this. And you can just chain those oscillators of different type. You can chain them to effects and get different results. You can also create analyzer node that can then produce also visual representation of your music. And I thought, okay, this is cool, so let me build my Groovebox. And that's what I did. So 4 years ago, I built my Groovebox in TypeScript. I first tried to build it in Angular. There were some performance issues. Then I tried to build it in some other frameworks, like Svelte, something lighter. Still didn't perform that well, so I ended up building it with plain TypeScript. And still there was some performance issues where the sound was simply dropping off. And the video that I posted on Twitter actually was like 6th or 7th take because it was already always missing a beat. So I had to re-record to make sure that at least these couple of seconds that I recorded looks okayish. And the problem back then was the timing. So just a little bit of math background. Let's say we are playing a song at 120 beats per second, beats per minute, which is basically 2 beats per second or 8 ticks per second because the beats are calculated in a 4/4 notation, which means that basically on every 125 millisecond, we need to figure out whether we play something or not. So with every 125 millisecond, your application needs to calculate whether it needs to play something, and if it needs to play, then it has to load the sound, calculate all the effects, append all the effects, and then play the sound. And this can easily go out of sync. Now, I was naively using set interval, which looked like this. So it was trying to run away while it was being chased by the rendering context, by the framework render loop, by audio context, and all the data processing that I was doing in the background. It was a complete mess. I found out that instead of using play immediately, like basically running the timeout, and then whenever it hits to try to play the sound, that I can actually schedule a sound ahead of the time. So if I just run the interval in the background and every time just schedule the playing, then I don't really care if it's on time or not. And it turns out that the audio scheduler is way more stable than a set timeout. Set timeout usually just goes out of sync because it doesn't really have to be on sync. But things like graphical buffer and audio buffer, they are really accurate. Now this did help a lot, but there were still performance issues. As soon as I was adding more and more tracks and more instruments, again, I was hitting some limits. So I was looking further, okay, let's see how we can improve this. And these are the learnings that I got from debugging that code and trying to optimize it. So I won't be talking about the standard lingo that you usually hear on conferences about performance, about the LCP, TTI, FCP, TBT, MBA, LSD. I won't be talking about hydration either, or partial hydration. And all of the examples that you will see and all of the results have been battle tested, and I have benchmarks to prove it. Now, when you start analyzing application, usually people talk about order notation and how to analyze the complexity of your code, and you usually look at the loops. How many loops I have? What is the depth of loops? Usually when you see something like this, how many loops would you say there are on this code snippet? So let's count it together. We have a for loop, right? That's 1. We have for each, that's 2. And we have for in, that's 3. But this one spread is also a loop, which is easily overlooked. And this can be quite heavy and quite expensive. Every time you're spreading or mapping over some values, you're basically running through the entire array or object, taking one item at a time and placing it in the new structure. And it's even worse because normal loops have just complexity of n, but spreading has complexity of n log n, because it's creating a new array, but it's looping over that new array again and again and again until everything is moved over. People say that mutations are bad, but in coding, they can be sometimes good. So let's look at this example. Let's say we have audio tracks and we want to unmute all the audio tracks at the same time. Now what we could do, we could simply use something like this, like spreading and mapping, where we take the tracks and we recreate them again by copying over all the fields and just changing the mute to false. But we can also do it like this, just set false immediately on the object. And we don't really care whether we need a new object. We can just use the existing object. And it turns out that this is 27 times faster just for the 10 tracks. The more tracks you have, the more speed improvement you get. We all know that repeating stuff is bad, and we shouldn't repeat the code, and we need to be reusing stuff. But this is also something that we easily forget. Like, look at this sequence. In order to initiate my track, my sequence has 16 steps. And the nodes usually have either value or they are false if they are switched off. Now, normally we would just initialize it to false so that we can read it in the UI and in our application, whether it's true or false. But we can also do it like this, because no value is the same as false value. So we can depend on our language's falsy values, such as undefined or null or just not being there. It turns out this is 50% faster, again, just for 16 steps. The longer the sequence, the more saving you get. Remember, no code is always faster than any code. You can always quote me on that. Let's talk about arrays and objects. Initially, when I started, my track looked something like this. So I had different fields like volume, reverb, envelope, my sequence. It was an object, because it's nice to work with objects. And then you would define your track like this. You would set up some values. And I was thinking, okay, what if I convert this into an array, where all these fields are just laid down as items of an array? Now you might think, okay, but come on, this is not readable, right? How can anyone know what that fifth element is? It just says false. But you can codify it. So each of the positions can have a unique name. So when you're accessing it, you're actually accessing it not by number, but by this constant name. So it feels ergonomically similar to using objects. You can still have strict typing on it. And the performance, 18%, not bad. What about lookup tables? Sometimes when we, for example, create tracks, a track can have a sample dedicated. And what I want to do is, for each sample that I find in a track, I want to see what is the offset of that sample, so I know how to play that note. So every time I have a sample, I need to find it from the list of samples to read its offset. And this can be quite slow. Now, better would be just to use some lookup table so that I can easily extract the information for that sample directly without looping through the array. This is 42 times faster just for 17 samples. Again, the more data, the more savings you get. Let's talk about maps versus hash maps. Again, we can have our structure that is in lookup table, in standard object, or we can have it in a map. It turns out that this is actually slower. But the caveat here is it's slower in this example when I tried it with doing not only get from the map, but also set into the map. And instead of having 17, having hundreds of samples, it turns out that map becomes faster. So it's important to not just blindly look at some small code example, but trying to understand what is my use case, how many data I'm dealing with, what am I doing with it. So these numbers are always questionable. You have to measure it in your own example. And finally, let's talk about higher order functions. Now, normally it's convenient to do something like this. Let's say we have a tracks, and then we need to filter only the sampler types. We want to map it to just extract the sequence, and then we run reduce to maybe combine it together. This is very readable, convenient, short, but it's also very expensive. We can do it like this, and it's 7 times faster. And again, more data, more of these higher order functions you chain, the slower it becomes. So whenever you care about performance, just forget about higher order functions. Because as you can see, not only the reduce, but also filter and map, they're basically doing what spread is doing. They're looping over the array to create a new array, both filter and both map. And they don't have just complexity of n, they have n log n. Now, when it comes to Angular, I was thinking, okay, there are new things now in Angular. Should I use signals or RxJS? Should I do zoneless or on push? How about no push at all? It turns out that the use case I have, I don't necessarily have to change the object and send it back from the parent component to child and back from child to the parent component. I can just drill down my sequence from the parent to child, change it on a child. My sound engine, since it's the same object that is being changed, my sound engine, when it comes time, it will read the proper data. And the parent component doesn't have to know what changed in the child component. Child component knows, and it shows the proper state. Parent doesn't have to know. And it turns out it's a tremendous amount of saving by not communicating states back and forth. Because if I would have to do it, like with onPush or something like that, I would have to use spread to change the object, to create new object, to send it back, and it would be just too expensive. So how are these things being monitored or measured? Usually I use tools like JSBench, where I can just place small code snippets, and I run them against each other to see what are the results. And sometimes there is a code there are parts of your code that you can't just extract somewhere else because they depend on some state or some backend. In that case, you can use console.time, where you can simply set the beginning position, the end position, and then console returns the time spent between those two positions. And this allows you to easily measure things. Now, you might be thinking, okay, yeah, but this only applies to this Groovebox that you were building. You cannot really apply it in the real world. Well, we use those same steps in NX to improve our ESLint. And it turns out, just by applying these small rules, very incrementally, we got 100 times performance boost. And you can read about it here in our blog post called Butterfly Effect. Now, enough talking. I promised Groovebox, so let's see how the full Groovebox looks like. So let's add some drum tracks. We can start maybe with some kicks. And I can then add some hi-hats. And we can, yeah, let's stick with piano. Again, we can do this stuff, and then we can add more things. We can add some claps. And since this talk is called Drum&JS, let's leave just piano playing for a second. Speed this to a proper drum and bass tempo. And let's change it just a little bit. Just like that, you can layer your sound and you can add tracks and tracks and tracks. All of this code will be shared online, so you can play with it, you can look how it was built, and maybe you can create your own cool samples and your own cool tunes. So remember, always know your loops, know how complex your code is if you care about performance. Don't be afraid to mutate your data. Mutation is always faster than creating new objects and new arrays. Choose your structures wisely. Skip higher order functions when performance matters. And check against your use case. But most importantly, always follow your passions. Thank you, and may speed be with you.